Dear students, so welcome back to Basil's Physics Classroom. In today's class, I'll be giving you a brief description of the chapter Thermodynamics. Okay, so when you deal with thermodynamics, the first term you should learn about is something known as a system. A system means it is an extremely large collection of a large number of atoms and molecules. Okay, now which is actually confined in a boundary. Everything outside this boundary, we will be calling it as a surrounding. So we have a system, we have a boundary, and we have a surrounding, right? So everything outside the system, we call it by the name of surrounding. Okay. Now, there are actually three types of systems. One, we have an open system. In an open system, there will be a transfer of matter and energy. Say for example, we have a cup of hot tea which is open. So there will be a transfer of matter there, and there is also a transfer of energy. Now, what if it is a closed cup? And we have the second system, a closed system. If it is a closed cup, there won't be any physical transfer of matter taking place there. But at the same time, there will be a transfer of energy, and such a system is known as a closed system. And the third one, it's an isolated system. Say for example, our thermoflask. There is no transfer of heat or matter with the surroundings. Okay, and please do remember that none of the systems around us is perfectly isolating in nature. So ideal behavior, it's not possible there. Okay. So we have the three types of systems: open system, closed system, and isolated system. Okay. Now, to describe a thermodynamic process, we make use of the so-called thermodynamic variables. Thermodynamic variables. Now, the thermodynamic variables include our pressure, temperature, volume, etc. Now, connecting these thermodynamic variables, we can frame an equation, and that we call it as the thermodynamic state equation. So, depending on the process we are dealing with, they will have different thermodynamic equations. Okay, so thermodynamic variables and thermodynamic equations. Alright. Now, if these thermodynamic variables do not change with respect to time, I repeat, if the thermodynamics variables do not vary with respect to time, then we can say that the system is in a state of thermodynamic equilibrium. So, to say that a system is in a state of thermodynamic equilibrium, it is necessary that the system has to be in thermal equilibrium, chemical equilibrium, and mechanical equilibrium. Mechanical equilibrium means that the net force acting on it should be zero. Chemical equilibrium means it should have a uniform chemical composition. And thermal equilibrium means it should be maintained at the same temperature. So remember that the thermodynamic variables, if it does not change with respect to time, we can say that the system is in thermodynamic equilibrium. Okay, so that is the idea about thermodynamic equilibrium. Now, just like I mentioned just now, we have different types of processes, different types of thermodynamic processes. We have isobaric process, we have adiabatic process, we have isothermal process, isochoric process, we have cyclic and non-cyclic process, we have reversible and irreversible processes, etc. So we'll come to these processes and the laws of thermodynamics once we learn a few other terms, very important terms. And the first term you have to learn is about Q. What is Q? The heat. What do you mean by heat? Heat means it is the energy transferred because of a temperature difference. It is energy transferred as a result of the temperature difference occurring. Now, this is actually a path-dependent function. Heat is a path-dependent function. And if you are considering a situation where the volume is remaining a constant, then we can say that delta QV will be equal to NCV delta T. Will be equal to NCV delta T. And if you're considering a situation where the pressure is a constant, we can write delta QP is equal to NCP delta T. So the first term I have introduced is known as heat. It is the energy transfer due to the temperature difference. Okay. The second term you should learn is about the internal energy. What is it? Internal energy represented by delta U. Now, internal energy means it is the energy possessed by a gas or something because of the molecular action and the molecular configuration. So when you talk about internal energy, it mainly consists of a kinetic and a potential energy. But in the previous chapter, when I taught you about kinetic theory, one of the basic assumptions that we took was that the potential energy was minimum, or we are not considering the potential energy into account there. Which means the internal energy will be purely kinetic in nature. So we can write it as delta U will be equal to 3 by 2 nRT or 3 by 2 P delta V. Okay, so the internal energy can be written as 3 by 2 nRT, where n is the number of moles. Okay, or for all gases, it can also be written like this: delta U is equal to NCV delta T. What is CV? CV is a specific heated constant volume. And I hope you remember what I taught you in the last class. CV was equal to what? R by gamma minus 1 into delta T, or F by 2 into R. Right? What is gamma? Gamma is known as the adiabatic constant. Okay. So that is about the internal energy. And the next term, it's work done. What is it? Work done represented by W. Now in general we can say that work done is actually equal to the integral of V initial to V final, initial volume to final volume, P dV. P dV. To represent the thermodynamic variables and the thermodynamic function graphically, we make use of something known as a PV indicator diagram. Okay, what is it? PV indicator diagram. So we will be able to actually determine what is the work done in a certain process if we are aware of the PV indicator diagram. Okay, say suppose I have a process like this. This is P and this is V, and a graph is given like this. Okay, now the area under the PV diagram, I repeat, the area under the PV diagram will give you the corresponding work done. Area under the PV diagram will give you the corresponding work done. Now suppose it is a cyclic process. Suppose it is a cyclic process like this. Okay, it's a cyclic process. Now, if it is a cyclic process which is given, the area of this particular cycle, the area of this figure, it's a triangle as you can see here, the area will give you the work done. And do remember that if it is a clockwise, if the cycle is moving clockwise, then the work done will be positive, and if the cycle is anti-clockwise, the work done will be negative. I repeat, if the cycle is clockwise, work done will be positive. The cycle is anti-clockwise, the work done will be negative. Okay. Now, suppose it is something like this. If the PV diagram is given something like this, and this point is P1, and this is P2, this is V1, and this is V2. Now, this is a previous year question which has been asked previously for your examination. And here, the work done will be given by pi by 4, P2 minus P1 into V2 minus V1. So, please do remember this also. Okay, very, very important. Okay, so I hope the PV indicator diagrams and how to find the work done from a PV indicator diagram is clear for you. Right? Now, let's move on to the laws of thermodynamics. So, first, we are going to learn about the Zeroth Law of Thermodynamics. Now, the reason it is known as the Zeroth Law, I'm sure you all know, because it was actually identified only after we defined the first and the second law. But without the Zeroth Law, we cannot explain everything else. So, it was named the Zeroth Law. Okay, now I thought the Zeroth Law is very simple. Suppose A and B are in thermal equilibrium with each other, and B and C are in thermal equilibrium with each other, then A and C will be in thermal equilibrium with each other. I repeat, if A and B is in thermal equilibrium with each other, B and C is in thermal equilibrium with each other, then A and C will be in thermal equilibrium with each other, and that is the Zeroth Law of Thermodynamics. Okay, now moving on to the first law of thermodynamics. There is a small difference from what you have learned in chemistry actually. Now here we are actually dealing with the work done by the system. We are not actually considering the work done on the system in physics. We are actually considering the work done by the system here. So because of that, this is a small difference. And here delta Q is equal to delta U plus delta W. Delta Q. The quantity of heat supplied is used for two purposes. One, for increasing the internal energy, and two, for doing some work. Now, when you learn about the first law of thermodynamics, there are high chances you're going to get a question using this. Okay? Sometimes it may be a direct question. But to answer this, you should know about the sign convention. So, what is the convention? Now, work done is taken as positive if the work is done by the system. So it will be negative if work is done on the system. Please remember that. Okay. Now similarly, the internal energy, change in internal energy will be positive if there is an increase in the temperature, and as a result the internal energy will increase. Vice versa, it will be negative if the temperature is decreasing, and as a result delta U will be decreasing. Okay, and delta Q, if a quantity of heat is supplied to the system, if a quantity of heat is supplied, taken as positive, supplied to the system or given to the system is taken as positive, and if it is taken or drawn from the system, it will be taken as negative. So these are the sign conventions you have to remember, and without these sign conventions, you will get the answer wrong here. Okay, so now let's move on to learn the thermodynamic processes one by one. So the first process we're going to learn is about the isothermal process. Which one? Isothermal process. As the name indicates, isothermal process is a process which takes place at a constant temperature. I repeat, it takes place at a constant temperature. And since it takes place at a constant temperature, we can write the thermodynamic state equation as PV is equal to a constant. Or we can simply write P1 V1 is equal to P2 V2. Okay. So thermodynamic state equation is PV is equal to a constant. Okay. Now there are two essential conditions you have to remember here for a process to be isothermal. The first condition is the walls of the container in which the gas is kept should be perfectly conducting. It should be perfectly conducting. Then only a free exchange of the heat energy can take place. So isothermal means temperature is a constant, right? So if the walls are insulated, there won't be a free flow of heat in the surroundings. So it should be perfectly conducting to facilitate heat transfer. And the process should take place extremely slowly, giving sufficient time for the heat exchange to take place. Okay, so that two conditions, please don't forget, it can come as a theoretical question for you, the two essential conditions. Okay, now the next point that you have to remember is about the specific heat of isothermal process. The specific heat of an isothermal process, C. Now we know that delta Q is equal to MC delta T, right? So from here we can write this is actually equal to delta Q by N delta T. Now here the temperature is remaining a constant, which means delta T will be, change in temperature will be 0. So 1 by 0 will be what? Infinity. Specific heat in case of a isothermal process will be infinity. Now let's apply float. What is float actually? Float is actually the short form for first law of thermodynamics. So So let's apply float over here. So applying float, what do you get? You know that delta Q is equal to delta U plus delta W, right? Now, since the temperature is remaining a constant, we can say that delta U, which is equal to mCV delta T. Delta T is what? 0. So delta U will be 0. Therefore, delta Q will be equal to delta W. Delta Q will be equal to delta W. Is the point clear? Delta Q is equal to delta W. Now, based on this, we can actually find out the work done also. So, what is the work done? The work done in an isothermal process is given by 2.303. You'll have to take the integral and everything. 2.303 nRT log P initial by P final. Or you can write it as 2.303 nRT log V final by V initial. That is another way in which you can represent it. So log V final by V initial. 2.303 nRT log V final by V initial is another way in which we can represent it. Okay. Now almost all the state changes. When ice is getting converted into water, water gets converted into water vapor, the state changes is an example of an isothermal process. Okay. Now when we draw a PV indicator diagram, we can actually draw a PV indicator diagram for this. It will be something like this, a PV indicator diagram. That is a PV indicator diagram for an isothermal process. Okay. And the slope of the isotherm, it is known as a isotherm, is given by dP by dV, which is the slope will be equal to minus P by V. Okay. Now here we can also define the isothermal bulk modulus of elasticity. And the isothermal bulk modulus of elasticity can actually be obtained from here. We can write minus dP by V I'm taking to the other side, so that will be dV by V. This is actually stress by strain, right? So this is actually equal to P. And this P, we call it as the isothermal bulk modulus of elasticity. Okay? So these are the main important points we have to remember in an isothermal process. Clear? Right? So now let's move on to the next one, and that is about an adiabatic process. Okay? So the next one is an adiabatic process. In an adiabatic process, what you have to remember there is basically, this is a process in which there is no heat exchange taking place. Which means the two essential conditions for an adiabatic process to occur are: 1. The walls of the vessel in which the gas is kept must be perfectly insulating. No heat exchange should take place. But I actually told you that none of the containers we have can be perfectly insulating, right? Therefore, one more condition we add on there. The process should take place suddenly. The compression or the expansion should take place suddenly, so that there is no time for heat exchange to take place. So what should be perfectly insulating, and the process should take place suddenly. Clear? Say for example, the propagation of sound wave in air, or a cycle tire suddenly burst, or sudden expansion or compression of gas in a container, or maybe the expansion of steam suddenly. Everything is examples for adiabatic process. So this tire bursting and everything, it can actually come for you in the questions. So by reading the question, you should be able to identify whether there is a heat exchange taking place. If there is no heat exchange, it's known as a adiabatic process. Okay. So the state equation for an adiabatic process is given by PV raised to gamma is equal to a constant. Another equation is T V raised to gamma minus 1 is a constant. Okay, we can actually make use of the ideal gas equation. PV is equal to nRT. Substituting, we get this. Okay. Another form is T raised to gamma, P raised to 1 minus gamma is a constant. Okay. So please remember all these three forms. It will come useful for you. Okay. Now that's the thermodynamic state equation. Now let's apply float. What was float? First law of thermodynamics. So applying first law of thermodynamics, what do you get? We know that delta Q is equal to 0. Therefore, we can write delta U is equal to minus delta W. Delta U is equal to minus delta W. Okay, and the specific heat is equal to, will be equal to delta Q by N delta T. Delta Q is 0, which means specific heat for an adiabatic process will be 0. Okay, now to find the work done, we know that the work done, the change in internal energy is equal to minus delta W, right? So while teaching the sign convention, I told you that if delta U is negative, that means there is a decrease in the temperature. If there is a decrease in the temperature, it means it's a cooling effect. It is a cooling effect coming there. Okay, so work done will be given by, or delta U, which is equal to minus delta W. Or I can simply write delta W is given by P initial, V initial minus P final, V final divided by gamma minus 1. Gamma minus 1. So what is this gamma I have been using here? Gamma, like I told you in the last class, it is known as the adiabatic constant, and gamma is equal to Cp by Cv. Gamma is equal to Cp by Cv. Okay. Now let's draw the PV indicator diagram. So drawing the PV indicator diagram, one thing that we see is the slope of the curve is actually more steeper than in case of an isothermal process. Therefore, when we found out the slope, we get that dP by dV is in fact equal to minus gamma times P by V. Minus gamma times P by V. And correspondingly, the adiabatic bulk modulus of elasticity, that is dP by dV by V minus of, is actually equal to gamma P. So here the adiabatic bulk modulus is equal to gamma times P. Clear? I hope these things are clear. So please make sure you remember all these points with respect to an isothermal and an adiabatic process. Okay? There are high chance you can get either question from either of them. Okay? Now moving on to the next process, and that is isobaric process. Isobaric process. Now bar, you have heard the term bar somewhere, right? The unit for pressure, right? So isobaric process means it is a process in which, or which is carried out at constant pressure. So the pressure is remaining a constant. So how do you write the state equation here? Pressure is a constant. We can write V is proportional to T. One of the gas laws we learned in the kinetic theory, right? So V is proportional to T, or we can write V1 by T1 is equal to V2 by T2. It is an isobaric process, and therefore the specific heat Cp is equal to gamma by gamma minus 1 into R. Or you can also write it as F by 2 plus 1 into R. F by 2 plus 1 into R. The Cp value. Okay. Now, we are going to apply the float over here. How do you apply float? First law of thermodynamics. Here the pressure is a constant, right? Pressure is a constant. So applying float, we get delta Q P is equal to delta U plus delta W, right? So here we can write delta U. What is delta U? We know that it is NCV delta T. And what is delta W? The pressure is a constant. We can write the work done is equal to P delta V. Okay, so here substituting we get this plus P delta V. Okay, now CV. What was CV in terms of gamma? N. Tell me. N R by gamma minus 1 delta T plus P delta V. N R delta T. You can take N R delta T outside. So you will be getting this as N R delta T. Within the brackets we have R, you're taking it outside. 1 by gamma minus 1 plus 1. What do you get? What do you get? Gamma by gamma minus 1. What was gamma by gamma minus 1? It is Cp. So you get this as gamma by gamma minus 1 into R is Cp. So you get this as Ncp delta T. It is Ncp delta T by applying float. Okay. Next is the PV indicator diagram of an isobaric process. For an isobaric process, the PV indicator diagram is given like this. It's a constant pressure process. The pressure is remaining a constant. Okay, so I think the points are clear for you, right? So in case you have any doubts, do comment below. Okay, now we are moving on to the next process, and that is the fourth one. What is that? Isochoric process. Now, isochoric process means it is a constant volume process. It is a process carried out at constant volume. If we are dealing with an isochoric process, then we can say that the pressure is directly proportional to the temperature, or we can write P1 by T1 is equal to P2 by T2. It is a constant volume process. Now we know that the work done is actually equal to P delta V, right? Work done is equal to P delta V. Isochoric, it is an isochoric process. So what will be the change in volume? The change in volume will be 0. Therefore we have work done is equal to 0. Therefore by applying float, we can write delta Q will be equal to delta U. Delta Q will be equal to delta U, and you know that delta U is equal to NCV delta T. Okay, so in an isochoric process, delta U will be equal to NCV delta T. Clear? And now to draw the PV indicator diagram, and before that, what is the specific heat here? CV, tell me, it is R by gamma minus 1 or F by 2 into R. Fine. And now the PV indicator diagram. Volume is a constant, so this is a diagram. The volume is remaining a constant in this PV indicator diagram. Clear? Okay, so I hope these four processes are clear for you. And now for a general process known as a polytropic process, I'll be actually doing a separate video for that. Okay. And one more thing, towards the end of the video, I'll be doing a graphical comparison of adiabatic and our isothermal process. So make sure you watch the video to the end. Okay. So moving on to the next one, that is about a cyclic process. Now, a cyclic process consists of a series of changes which brings the system back to its initial state. So a cyclic process is a process in which the initial and the final state of the system is the same. But in a non-cyclic process, that is not the case. Okay, which means if you find out the internal energy, the change in internal energy, which is actually a point function which depends only on the initial and final point. It does not depend on the path taken. So delta U will be corresponding to 0 because the initial and the final state is the same. So delta U will be equal to 0 in case of a cyclic process. Now when we apply float here, what do you get? So delta Q will be equal to delta W, and that means the entire heat given will be converted into work in case of a cyclic process. And another point that I previously mentioned was that if we are drawing a PV indicator diagram for a cyclic process, if the cycle is clockwise, the work done will be positive, and if the cycle is anti-clockwise, the work done will be negative. Okay, and for a non-cyclic process, it is again given by the area under the graph, corresponding portion. Okay, so do remember about a cyclic and a non-cyclic process. Okay, so just remember cyclic, and once you remember cyclic, you can actually answer the corresponding conditions for a non-cyclic process also. Okay, now another term you have to learn here is something known as a quasi-static process. What is it? Quasi-static process. Now, quasi-static process is a process which takes place extremely slowly. Such that each and every single state during the process will be in a state of thermodynamic equilibrium. I repeat, it is a very slow process such that at each and every single state it will be in thermodynamic equilibrium. Okay, so that is a quasi-static process. And the next one is a reversible and a irreversible process. What is a reversible process? A reversible process is a process which can be reversed by repeating all the changes in the direct process in the opposite order. So by doing that, we can actually retrace and come back to the initial thing. Okay, so that is what we mean by a reversible process. And a process in which the retracing is not possible, we call it as an irreversible process. So I hope it is clear about a reversible and a irreversible process. Okay, so remember these terms we have learned: cyclic process and non-cyclic process, reversible and irreversible process, and also the quasi-static process. Okay, now let's move on further and learn about what is a heat engine. What is a heat engine? Now you will be learning about a heat engine and a heat pump. First, let's learn about a heat engine. Okay. Now to learn about a heat engine, you should know about three entities. One, something known as a source. A source will always be kept at a very high temperature. It is at a reservoir. It is kept at a very high temperature. And then we have something known as a sink. A sink is kept at a lower temperature, and it is capable of accepting everything that we throw into it. Okay. Now, one more thing is there. There is something known as a working substance. In a heat engine, the working substance may be gas or steam or something. Okay. So now, what is happening here? Let me tell you. Now here, what is going to happen here is, from the source, some heat will be taken, and utilizing a part of the heat, some work will be done. Utilizing a part of the heat, some work will be done. So we can say that the work done will be equal to Q1 minus Q2. The heat taken is Q1 from here, and Q2 is the heat given to the sink. So work done will be equal to Q1 minus Q2. So we can define the efficiency of a heat engine like this. Efficiency is equal to the work done by the quantity of heat supplied or the heat given. Work done by the heat given. Or this is equal to Q1 minus Q2 divided by Q1. Or this is equal to 1 minus Q2 by Q1. Or we can also write it like this: 1 minus T2 by T1. So the efficiency of the heat engine is given by 1 minus T2 by T1. Okay. Now we do prefer a heat engine with 100% efficiency, or when eta is equal to 1. But that is not a possible case. Only one thing is possible. Efficiency will be always less than 1. Okay. It cannot be 100%, it will be less than 1. Okay. The point is clear, I hope. Right. But at the same time, theoretically we have an ideal heat engine. And that ideal heat engine we call by the name Carnot engine. And the cycle we call it by the name Carnot cycle. Okay, so let me tell you what is a Carnot cycle. Now in a Carnot engine, there are mainly 4 processes involved. So I'm going to teach you what is a Carnot cycle and a Carnot engine. The first process is actually called Isothermal Expansion. What is it called? Isothermal Expansion. Second step, it is known as Adiabatic Expansion. And the third one, it is Isothermal Compression. Isothermal Compression. And the fourth one, we call it as Adiabatic Compression. Now I'll give you a brief idea about the 4 processes and how it works out. So let me draw a PV indicator diagram here. It's a PV indicator diagram. Okay. Now I have 3 things here. I have a source here. I have a isolating pad or insulating stand here. And here I have a sink. So here the first process what we are doing is, we will be taking I'm taking a cylinder piston arrangement. Now the walls of the cylinder will be insulating and the top surface is also insulating. The only conducting phase is the lower one in contact with the source. Okay. So now initially we will have a working substance, maybe some gas, maybe an ideal gas here. And it is an ideal gas. Why? Because this is an ideal process. So we are taking an ideal gas over here. Now what happens is, the first step, isothermal expansion. Now what is actually happening there is, from the source, some heat will be given to the system, and using this heat, this piston will be moving up. That is, there is a change in volume taking place here. If the volume was remaining a constant, because of the input heat provided by the source, there would have been an increase in the temperature. But by ensuring that the piston moves up, the increase in temperature will be compensated for, and therefore there will be an isothermal expansion taking place there. So first step, it is an isothermal expansion. So normally we denote the temperature for source as T1 and sink as T2. Okay, do remember that. When we learn a refrigerator also, T1 and T2 representation remains the same. Okay, that will be useful when you do the questions. Okay, so first step, it is an isothermal expansion. As you can see there, the pressure decreases and the volume is changing, increasing. Okay, that's the first step. The second step, what we're going to do is, we're going to take this arrangement and keep it on top of the insulating pad. Now you know what is going to happen. Now again, it is insulating. Already the walls were insulating, the top surface was insulating. Now the bottom face is also insulated, which means utilizing the energy available inside, it will continue on its expansion. So there is no heat exchange taking place, and we can say that it is an adiabatic expansion taking place there. So we know that the slope of an adiabatic process is greater than that of an isothermal slope. So here the temperature changes to T2. There is a change in temperature to T2. Okay. Now you know what we are going to do? We are going to take the sink. We are going to take the cylinder arrangement and place it on the sink. Place it on the sink. And now we will be doing some work and compressing the piston down. We will be compressing the piston. So what will happen? The volume decreases, and as a result of the decrease in the volume, the temperature inside will be increasing. But the process will be carried out in an extremely slow manner, such that the whatever is the increase in temperature here is given to the sink, which means there is a compression taking place here, there is an increase in temperature, but all the increased energy is given to the sink, which means it is an isothermal compression that is taking place here. It is an isothermal compression. So now isothermal compression, so the temperature is again remaining a constant. Isothermal compression. Okay, now again we take this and place it over here on the insulating stand. Now what do? We again exert a force and compress the piston. We again am compressing the piston. But now there is no way for the energy to escape out. It is on an insulating stand, right? What happens? The temperature rises back up to the initial value, and that is our T1. It rises back to here. So this is the so-called Carnot cycle. So this is the so-called Carnot cycle, and we have the Carnot cycle taking place here. Okay, so this is an ideal process. For a Carnot engine, the efficiency, for a Carnot heat engine, efficiency is equal to 1. But that cannot be realized in practice. Okay, and one thing I forgot to mention here is about the second law of thermodynamics. In fact, there are two statements for second law of thermodynamics. We have closure statement and we have Kelvin-Planck statement. And we also have a Kelvin statement there. Okay, in fact, three statements are there. Now, closure statement and Kelvin statement, the general idea is, without doing any work, without doing an external work, it is impossible to transfer heat from a cold body to a hot body. That's the basic idea. I'm not giving you the detailed description of the two laws. Please go through your NCERT, your reference books, whichever you're using, and learn the two laws, okay? The second law of thermodynamics put forward by Closius and Kelvin-Planck. So the basic crust idea is this: it is impossible for a body to transfer heat from a cold body to a hot body without doing some work. And one more thing, the heat that we are giving will never be used or will never be converted fully into the work done. There will be some losses. Okay, right. So remember that about the second law of thermodynamics. Okay, so I hope this concept of Carnot cycle is clear for you, and with this know-how, let us proceed further to the next one, that is about a refrigerator. Okay, now in a refrigerator, device in which the exact opposite of what took place in a heat engine takes place. It is otherwise known as a heat pump. Heat pump. We know that in a heat engine, heat was taken from the source and given to the sink. Now here, the heat will be taken from the sink and we'll do some work and then reject the remaining heat into the source. So it is actually working in the opposite manner in which a heat engine is working. Okay. Now here again we can define the coefficient of performance of a refrigerator represented by beta. And beta is given by the heat extracted by the work done. So this can be written like this: Q2 divided by Q1 minus Q2, or you can write it like this: T2 by T1 minus T2. So we have the expression for beta and we have the expression for eta, so we can relate both, and beta is equal to 1 minus eta by eta. Please remember this equation, very important equation from exam point of view. The relation connecting coefficient of performance of a heat pump and that of a heat engine. Clear? So I hope the refrigerator and Carnot engine is clear. So I have just given you a brief idea about Carnot engine. I have not talked to you about the work done equations and everything. So please make it a point to learn those equations also. Okay, there is no specific equations as of to learn there, because it is an isothermal and an adiabatic process taken there. So isothermal work done, you're already familiar with that, and an adiabatic work done equation also you're familiar with that. Okay. So I hope you were able to follow till here, right? So now we move to the last one, that is about entropy. Okay. Entropy is actually a measure of the disorder of a system. Now, greater the disorder of a system, greater will be its entropy. It is represented by ds or delta S. Okay. Now, it actually gives you, this is actually known as the mathematical form of the second law of thermodynamics. Okay. And according to this, we can write ds is equal to dq by t. dq is known as the heat absorbed by the system and t is the absolute temperature. And do remember that at equilibrium, the entropy will be maximum. Okay. And suppose we are taking a solid or a liquid, and the heat given to the system is used for a state change. Okay, then we can say that the corresponding entropy will be equal to ml by t, where L is the latent heat of vaporization or fusion, and positive means that it is the heat absorbed. If it is a heat rejected means or heat evolved, it will be negative. Okay, and if because of the heat supplied, the temperature changes from T1 to T2, then we can say that the entropy will be equal to 2.303 mcc is the specific heat, that is the mass, log T2 by T1. Okay, and for a perfect gas, a relation between T and V in terms of entropy is NCV log to the base E. This log to the base E, okay, not to the base 10. T2 by T1 plus NR log to the base E, V2 by V1. Clear? So this is about entropy. So I hope the chapter is clear for you, thermodynamics. So in case you have any doubts with respect to the chapter, feel free to comment below. I'll be very happy to help you out with. And in case you need any other chapters, do tell me, I'll take it for you. Okay, so please do subscribe to the channel and make sure you share it with your friends. Okay, so once again, thank you.